right, folks, we got this. Day 3, completing the square for equations of circles. You might notice this here. You might notice this introduction is actually very, very similar to the last lesson we did yesterday, which I believe was lesson number, what are we up to now? Lesson number 18 yesterday. We're in lesson number 19. Yes, we are. So anyways, just some background on this. I'm kind of giving you the same lesson twice. They're different problems, but I want you to be kind of walked through how to do this process. The technique of completing the square to rewrite the equation of the circle from general form to graphic form. So sometimes, right, a certain textbook, a certain way of doing things will work for some people, and then other approaches will work for other people. Okay, so this is from the same kind of textbook source, but they're two different lessons that are supposed to teach the same thing. So if you already learned this, if you feel pretty confident after yesterday's lessons, still do it again. You'll still knock it out. You'll get good practice. If you had trouble, if you found yesterday's lesson being particularly challenging, then you have another approach to hopefully figure it out on this one here. So let's read through the introduction to hear what you're going to do today, and then let's just work on these problems. We'll get them done. This will be hopefully a much shorter video than yesterday because I gave you some background into completing the square and writing things from general form, changing that into the graphic form where you have two complete squares, a binomial with x in it and a binomial with y in it. And then that's equal to the square of radius, right? That's the whole graphic form thing. So let's do this today. In the last lesson, you applied the Pythagorean theorem to write the equation of the circle in graphic form. Perfect. Given its center and radius. You actually did that 2 lessons ago. In this lesson, you will use the technique of completing the square to write the equation of the circle from general form to graphic form. So kind of a review of what you did yesterday. And we'll make sure you get this one and make sure you know how to do this super special, super awesome skill. Let's get going, guys. Question 1214, like parabolas in algebra 1. There any more than one form. Perfect, right? We saw that in great detail last lesson. So we're not going to do algebra 1 stuff today. It looks like we're going straight into geometry stuff here because we have a circle relationship on a graph. Write the equation of a circle graphed at right in graphing form. X minus h squared plus the quantity y minus k squared is equal to r squared, as you did in the previous lesson. What's the parameters h, k, and r represent in graphic form of the equation of the circle? Well, this is the easy stuff. See, sometimes teachers, they teach you the stuff you have to know, because you have to know how to do this. But then they teach you slightly harder stuff, because the harder stuff is going to make you remember the easy stuff here. So this, you're just, this one is so easy, and just give me the hard stuff. To be honest, you really don't need to know the hard stuff super, super well, unless you're taking the PSATs or maybe the SATs. Because no teacher at Lowell is a geometry student, so give you questions on completing the square and writing in general form to graphic form, but they will give you questions like this. So anyways, you know how to do this here. We got this here. Our h is going to be 3. Oops, sorry. Yes, it's going to be 3. And our k is going to be 1, because 3, 1 is where our center of the graph is going to be. And then 5 is going to be our r. So we can complete this here. X minus 3, right? We're offset 3 to the right, so if we plugged in 3 here, we get 0, right? Get 0, 3 minus 3. That's why we know it's going to end up being the center. And then we got plus y. And, right, remember, I've drawn this out several times here. This here would be the x-coordinate, minus 3, and this would be the y-coordinate, minus 1. That's why we subtract the 1, not add the 1 here. And leg squared plus leg squared is equal to the radius squared. And the radius here is 5, so put here 5 squared. And again, I don't like doing that. I like putting it out actually squared here. Okie dokie, we got this in graphic form, and then HK is the center, and R is the radius. And I wrote mine as the square of R. Right? And just typically the way it is written here, it's usually not written, it's 5 squared. You really do either one, but typically you square it and show it there. So you just kind of want to take the square root to verify that is actually the radius of this is 5. Now we write the equation of the circle part A in general form. There we go, general form. So general form, you have the same number of x squared terms as we have y squared terms, and that's what's going to make it a circle. That's the special sauce there, right? You'd have, for a given input of x, you'd have 2 solutions for y. For a given input of y, you would have 2 solutions for x, except for the points that are on the extremes of the circle. So here, we had 1 x input. So a horizontal line here, vertical line here would be tangent to this point here. That would be at -2, 1. there's only one output. But at -1 for x, there are two outputs here. So the squaring thing is kind of what makes it so it's not a function, and so we have to have the graph would have to go on top of itself at some point. And then having equal amounts of x squareds and y squared, that's actually going to make it perfectly symmetrical, and symmetrical both with the x-axis and y-axis, and perfectly circular. So if you have different amounts of x squareds and y squareds, it's a different shape, which you can see. You can play around with Desmos a little bit. You might get an ellipse, you might get like an oval looking thing, or something else. Anyways, let's change it to general form here, and let's maybe do it in our heads here. X minus 3 squared, that is x squared minus 6x plus 9. Y'all know this, that a perfect square here, a perfect square of a binomial, well, binomial being squared here, x plus b, a plus b. This is actually a shortcut here to distributing out perfect squares. A plus b squared equals a squared plus 2ab plus b squared. So that's just a rule to keep in mind so you make this go a little bit faster distributing out here. So a plus b squared equals a squared plus 2ab plus b squared. And the reason for that is because a plus b squared isn't just a squared plus b squared, it's a plus b. It's this whole base times itself, a plus b times a plus b. So at the end of the day, right, if you were to FOIL this, first would be a squared, FOIL, right, F-O-I-L, outer would be ab plus ab, and then inner would be plus ba, and we can write BA as AB because when you're multiplying, order doesn't matter. And finally, last for FOIL, F-O-I-L, FOIL, we have B squared at the end here. So this is just a shortcut here. When you know something is written in this form, the quantity A plus B squared, or it could be a subtraction too, that's fine. You can just write out your answer as A squared plus 2AB plus B squared. And that's what I did in this first one here, x minus 3 squared. So if we squared it, we'd have an x squared as the first term, and then we would have plus 2ab, and 2 times by x is 2x, and then b is -3, so 2 times -3 is -6, and then we have -6x here, plus b squared, and b is -3, and -3 squared is +9. Anyways, let's apply that to the next one here, and you can always just set up a generic rectangle, multiply. I don't have to do it the way that I'm doing it here. And y minus 1 squared would be y squared minus 2x plus 1. And this is equal to 25, as we saw earlier. Okay, so then just to get it into general form is we got to order it by the x terms go first, and you're ordered by the exponent. So ordered by exponent is technically how you should think about it first, but put x terms before you put y terms. So I'm going to put x squared here plus y squared. So here I have my ax squared term. A here is 1. A here is 1. Good. We know it's going to be a circle. And then I'm going to put my bx next. So x comes before y. So we get -x, 6x. And then we have our y over here. Oops, this should have been -2y. So minus 2y. And finally, our constants, right? We want to have our values on the left side of equals here. So we need to move this 25 out of here, make a 0 on the right side so we get it in general form. So I'm going to subtract 25 from both sides. And then I'm going to have a constant of 9 here. We had 1, so that's 10, and then minus 25 is -15. Was that the same exact problem as it was in the last classwork? It might have been, because I think they wrote this textbook wrote this lesson in their older textbook, and then they tried to revise it. They tried to make it a little bit more approachable, a little easier, and that's why they had all that Algebra 1 review, because they thought doing this stuff right away was a bit too harsh for you geometry students who maybe have not taken Algebra 1 in quite some time. Okay, so then here we get into this idea of completing the square to go from, well, the last one we went from graphing form to general form. Part C is going to say, how can we do the opposite? How can we go from general form to graphing form? Question mark. Do you remember doing that yesterday? So how can the process be done backwards? For example, if you're given the equations such as this one, how can you change to graphing form? Discuss with your team and consider the work you did yesterday in lesson number 18. So here's how I was doing them yesterday. I'll go through them again if you just want to follow my process for it. So we need to complete a square involving x. So I'm going to put x squared plus 4x over here on the left side. Then I'm going to have some space so that I can complete the square. And I'm going to do plus y squared plus 2y And then I don't have any constants on the left side. That's nice because I want my constants in graphing form to be on the right side because that's where my radius, the square of the radius, is going to end up being the constant on the right side. So let's complete the square, and completing the square involves adding values to the left side and equal amounts to the right side. So here, if I'm going to complete the square, x plus, and remember we divide, if you want to figure out what the complete square is, we divide the b by 2. If we have an a here of 1 and an a here of 1, the trick is you divide your b, your ax squared plus bx plus c. We don't know what c is yet. We need to add to get to c. But we divide our b by 2, and that's going to tell us what our perfect square we're looking to complete is. The perfect square we're looking to complete is x plus 2 squared, and that would have a constant of 4. 2 times 2. 2 squared is 4, and that's what we'd have to add to the left side. If you're adding 4 to the left side, you got to add it to the right side. And then next one is right here. And this, I'm going to divide my b by 2, and I'm going to have y plus 1 squared. That is the perfect square I'm looking to complete. This is an incomplete square. We don't have a constant term here, right? This is a incomplete square. I can't factor this. Let me see if you can factor out a y, but yeah, this isn't a perfect square trinomial. So we need to figure out what the third term is going to be. And that's going to be equal 1 because half of the b term is 1, and then square it, that gives you the c. You had to have 1 to both sides. And this might be the same exact problem as you had yesterday. This is 16. Okay, so there's our graphing form, and it says state the center and radius of this action here, what you just did. This is the same, identical, right? Using work above, we knew the general form, but we can get it to graphing form to state the center, which is -2, -1. You got to switch those signs. And radius is 4. All right, so now that I got you working harder, right? It's just you take a deep breath once you get to a question like what's the center and what's the radius. This is kind of hard for people to read. Like it's just something you memorize for an average geometry student. But if you're working harder, right, you need to know this, right? You need to know this because you need to work for it, get there. So that's my whole idea about this. If I make you work hard for this stuff, well, one, you might be able to answer a question like this on the PSAT or SAT, but also, when you get just asked, hey, where's the center and radius of a circle written in graphing form? You're like, oh, that's the easy thing. I got this. Okie dokie, Jessica's back here again. Jessica's working on rewriting this general form. Circle, we know it's a circle because we have an equal amount of x squareds and y squareds. In graphing form, but doesn't know how. She thinks that she needs to start by moving the terms with x in them next to each other to add the 3 and to add the 3 to both sides. I agree with her. So it looks like this is just kind of hand feeding you the process that I recommend for doing this. Did I rewrite this one? I may have. I don't know. Hey, do it this way because this is the way I model it for you, and it's easier when you can do it the way the teacher is doing it because you can practice along with him or her. And this is y squared, and this is 6y. We need to add 3 to both sides because we need to get rid of that 3. Add the 3 to both sides. So really add the 3 to get rid of a -3. That's what that means. So we'd be left with 0 for our constant left side, and then we'd have a 3 constant on the right side. But that's not going to be related. It's going to be part of our radius, but not a crucial part of our radius. Okie dokie, let's figure out what perfect squares I need to do. Well, this is kind of similar to up top here. Half of b is -2. -2 squared is 4. So we need to add 4 to both sides. And our perfect square here for the x, as far as the x's are concerned, are x minus 2 squared. And then let's do this for the y part here. Oops, I got to put a plus there. Did I put up a plus there? I did. Y squared plus 6y. Well, the perfect square we're looking to complete is y minus 3. So it's really quick. You can be really quick to figure out what the center of this circle is. And they're not going to ask you for this. So maybe they'll ask you for it. Let's see here. So center, I might even write down here, because the center is just going to be half of what our, is it B? What do they use to label it here? B, half of the B and half of the C, right? So half of the B squared is going to, just half of the B is going to be the opposite of the x coordinate, and half of the C is going to be the opposite of the y coordinate. So, right? Half of this here goes into your perfect square here. So your center is going to be at +2 and then +3 for the y coordinate here. So, right, you just by eyeballing the graphing form, divide that by 2 and then take the opposite sign, and that's going to give you the coordinate that you need for the center. Okie dokie. So in order to complete the square, to change y squared plus 6y into y minus 3, the quantity minus 3 squared, we need to add a constant of plus 9 over here. And oops, I made a mistake here. This should have been positive 3. So this center should have been at negative 3. 2, negative 3 is where the center of that circle is. Add 9 to both sides. And then we can combine like terms over here. 7 plus 9, 16. And it looks like we have another radius of 4. Is this the same exact problem I gave you yesterday? I'm not sure. Remember, it's the same people who wrote these problems. They just changed up the order. They changed how it's presented to you. So it doesn't matter. I think it's good practice to do the same exact problems over again. And then hopefully you feel like you understand them a lot better. How can Jessica complete the squares on the left side of the equation while keeping the equation balanced? Well, add equal values to both sides. So she didn't have any constants on the left side after she did this here, after she moved x squared minus 4x next to one another and moved the negative 3, added 3 to both sides. She didn't have any constants on the left side. So what she needed to do is she needed to make this left side bigger so that she could write these as perfect squares here and here with the binomial being squared. So if she needed to make the left side bigger, she just needed to add the same amount, add equal values to the right side, the same amount to the right side to keep the equation balanced. And then she can factor into her graphing form. And she can easily tell what the radius is here. Write the equation in graphing form and sketch a graph at right. Be sure to state the coordinates of the center and the length of the radius. Well, I've already written it in graphing form, so I'm going to go and circle this and point this out to you that I've already done this here. No reason to spend the time rewriting this out because it's painful writing with this computer pen here. And then let's go ahead and sketch a graph here at right. So our center is at 2, negative 3, which would be down here. And then our radius is 4. So I might put a point here, might put a point here, and I might put a point here at 1. 2, 1 would be on there. And then if this is negative 3, I could go down to negative 7. Okay, and then sketch a graph. So I'm not even going to use that circle tool. I'm just going to sketch it. Give myself a C plus on this one. No, I'm going to put this in BCAT. That's a solid B looking circle right there. B looking circle. So if you're going to sketch this out, maybe you just indicate that radius equals 4. And then this point here is at 2, negative 3. And we're good to go. We got this sketched out. All right, so let's help Jessica's older sister with her problem. We got question 1216. Jessica's older sister, Tisha, is taking pre-calculus and is stuck on a homework problem that asks her to determine the points of intersection between the two circles at right. Now, I know what you're thinking. Hey, I'm just a geometry student. I'm just an algebra student. How can I help with pre-calculus? Well, hey, pre-calculus is kind of like a lot of review of the earlier algebra stuff. You can kind of think of it, right, before you take algebra, you take pre-algebra. And that is just kind of reviewing everything you need to know before taking algebra. Pre-calculus, hey, it's just going to review some geometry for you, review some algebra for you. It'll be all good. You got this. So you'll practice this pre-calculus problem right now. So anyways, we have here determine points of intersection between two circles at right. So we have here one equation. We have here a second equation. So this is kind of a systems problem. And I put systems down because a system, what a system is, you should have studied this past year in Algebra 1. But a system is two or more equations, or they could be inequalities too, two or more relationships that share variables. And normally you can find some common solutions between those two equations. And here we have one equation here, we have another equation here. And we're going to see if there are points of intersection between the two circles at right. So what we mean by this here is common solutions. Values of x that are going to return the same y in both equations. So if we plug an x in, for instance, to one equation, we would solve for y and get the same solution, or solutions, right? They're likely going to be 2 for a given x in the second equation, because these are circles, right? We get 2 y's for an x and 2 x's for y, except for the really extreme points horizontally and vertically on the circle. Okay, we know that these are circles. These are both in general form. Again, inspecting the anatomy and the structure of this, we see we have an ax squared of 1x squared, and we have an ay squared of 1y squared. So we know we have the same number of x squareds and y squareds. We know it's going to be a circle. We know this is going to be a circle too, because this is all we're really studying is when our a is 1 for both of those. Okie dokie. So Looks like Jessica's going to help her older sister on this because she's in geometry, friends. She's been studying this stuff recently. You're going to figure out the intersections by using your knowledge of completing the square. Okay, so it sounds like she's going to do this algebraically. Rewrite the two equations. Oh, actually, algebraically changing it to graphing form, it looks like you're going to have to do. And then you're actually going to solve this by a graphing method, actually seeing what the intersections are on a graph. So it says here, use Jessica's method of graphing to determine the points of intersection. So this is solving by graphing. And with systems, right, there should have been ways you studied this past year for solving a system. One could be solving by graphing, just graphing the functions out or the relationships. Here, these are relationships. You're going to graph circles, which are relationships and not functions. So you could solve a system by graphing. And then there were algebraic methods of manipulating the equation 2, 3, and 4. At least I teach 4 ways, which maybe we'll have to use those later to also confirm that our answers are correct. Okie dokie. So let's move our equations down here. And with moving these equations down here, notice that I kind of set it up to complete the square. This is how I solve problems like these. I save space to complete the square on the left side, and then I move my constants over to this side. So if I have negative 12 over here, I have to add 12 to both sides because graphing form has the radius on the right side. So we want to start figuring out what the radius is. General form has all terms on the left side set equal to 0, and you start moving them over. So there are no constants in system or equation number 2. There isn't a constant, right? A constant is a term with a 0 exponent for the variable. So for instance, 5x to the 0th power could be a constant, and that would just simplify to 5. So constants can be thought of as just numbers, normal counting numbers that we usually see, or decimals with no variables next to it. So that's what I mean by constants. We added 12 to both sides. We have this here, and I save space to complete my x plus b squared and my y plus x squared or y plus z squared or whatever, however you want to call it. I mean, our goal of this, remember, is to complete the square. It's really just one step. We want to write something relating x plus some other number or minus some other number squared, and that's going to tell us where our x coordinate is of the circle. And then we want to write y plus or minus something squared, and that's going to equal this is going to tell us what the y coordinate is of the center of the circle. And this is going to be equal to the radius squared. And we want to figure this all out. And we can just do this very quickly right here, okay? What's half of 4? That's 2. Square 2, you get 4. So you have to do this to complete the square y plus 2 squared. That is our trick. And again, you can set up a generic rectangle if you want to. And I call them generic squares for stuff like this because you're building out something that has equal width, x times x. This has equal width to height so far, but then I need to break up my 4 x's. I can put 2 x's here and 2 more x's up here. So the perfect square you're trying to create is x plus 2 times x plus 2. And the missing constant in this situation would be 2 times 2, which is 4, right? We get that from what's half of the b coefficient here, and that's 2, square it, and you get 4. That's what we need to get to, okay? So we added 4 to this equation on the left side in order to complete a perfect square trinomial, right? This is a perfect square trinomial because x squared plus 4x plus 4 is equal to its product, which we see on the outside, x plus 2 squared. And the way we can complete the square is we originally didn't have that, right? We originally didn't have that plus 4 in the original equation number 1. So we need to add 4 to both sides in order to get there, okay? So we have 16 now on this side. Does that mean the radius is 4? No, we haven't completed this square over here. That's going to tell us, hey, our center here is going to be at, for 1, our center is going to be, we know part of the center so far, and that's going to be at -2 for our x coordinate. We need to get our y coordinate. So here, what's half of -6? Oh, that's -3. Square -3, so -3 times -3. 2 negatives make a positive. So I'm going to add 9 here, and then I got to do that to the other side. So I get y minus 3 squared, because -3 squared is 9, and -3 plus -3 is -6. We'd have -6y's if we foiled this on out, or use a generic rectangle to confirm our answer is correct, okay? So now I have 16 here. We added 9 to it. Perfect. That gives us 25. So that means our center here is going to be at -2, 3, and our radius is going to be 5. All right, we're on to number 2. Let's maybe use a different color. Actually, let's sketch this out. Let's get the graph sketched out, and then maybe I'll use the circle tool so we can get a nice, precise answer. So I'm going to find my center. at -2, up here at 3. And now I'm going to use my oval tool. So maybe you'd use a compass if you're doing this on your own to get a radius of 5 here. -2, 3 is going to be where the center is, and then a radius of 5. Needs to be much smaller than this. And that looks pretty good. Looks like I have a point here at 3, 3, which would be a point because that is 5 away from -2, 3. 3, 3 is 5 away from -2, 3. So I have my radius of 5 here in all directions from the center point at -2. Got a point here at -2, 8, which is 5 away from -2, 3, right? 5 above -2, 3. So let's get this other one. Let's do it in a different color. Let's do this funky green color here. Half of -8 is -4. Square it. 16 is what's going to complete the square here for the x term. So we're going to get x minus 4, square it up, and we got to add 16 to this side as well. Very quickly, let's get this one done. Half of -6 is -3. Square it, and that's going to get +9 right there. Add 9 right here. And look, we're going to have a radius of 5 here as well. Because, well, first things first, let's make sure we factor this perfect square trinomial. Again, it follows the form that I showed you earlier. A squared plus 2ab plus b squared. Our a would be y. Our b would be the square root, which is 3 or -3. So -3 times y, and then double it is -6y, gives us that middle term. So this is x minus 3 squared. And this is going to tell us the information we need about our second circle. Center at 4, 3, and radius is also going to be 5 because the square root of the constant we have here, that's your radius. Let's get this circle graphed. So one thing I notice here is that our y values of the center are going to be the same. We have the same radius, so these are going to kind of be nicely overlapping here. Here, what I can do to actually graph this, which would be good, is to duplicate. I wonder if I can do that, if I can duplicate this circle. Copy, paste. I can. And then I might just change the color so that we know we're talking about the green graph. Ah, yes, I like this. And so now I have a center at 4, 3 right here. Look at that right here. This is 4, 3 is my center. And now I'm going to figure out what my intersection is. So I like the idea of changing this to green so that we can compare. Here's circle number 2 is this one. The one in green here, centered at 4, 3 with radius of 5. And the other one is the blue circle. Equation number 1. Is the blue circle, okay? Do we find what our solutions are? Let's see if we can get our solutions. Well, it looks like approximately, we might want to double check our answers. So using Jessica's method of graphing to determine the points of intersection, it looks like our solutions, points of intersections, or what we're being asked to find, are going to be what we see in red up top here. And it looks like we have, if x were to equal 1, then y would equal -1. And that's going to be true in both equations. And then if x were 1, y could also possibly equal 7. Could also possibly equal 7. So you could double check in this equation. Let's just quickly do one in our heads. Let's do 1, let's see if we get -1 for y. So let's plug in 1 for x and -1 for y here. 1 squared plus is 1, right? And then 4 times 1 is 1, so that's 5 minus -1 squared would be +1, so -1 is 4. And then we have to add 6 to this here. So wait, 5 -1 squared is 1, but subtracted. Yeah, that would add 1, right? We're subtracting. Does this work? I don't know if this works. I don't know if we got the right solution here. We might have to algebraically solve this in a second, but it looks pretty darn close to being correct. Oh, that's a plus. I see what we did wrong. This is a plus with y here. So this isn't negative. I just drew this circle kind of awkward. This is plus. So we'd have 1 plus 4 is 5. Plus 1 is 6, and then minus a -6, because y is -1, that would be 12. Minus 12 equals 0. So yes, 1, 1, -1 is the solution at the top. Let's see if it's the solution at the bottom. 1 squared is 1, minus 8 is -7, plus -1 squared is +1, so -6. And then add 6 there, because -6 times -1 is +6, and that brings us to 0. Yes, this solution is correct, and therefore we assume that solution is correct, which we're pretty darn confident about because these are circles. You're going to get 2 solutions here. We could plug in 7 for y, And the same thing would end up being true as if we plugged in -1 for y in the problem. Anywho, Tisha thinks that there's another way to do this. So first one we did was solving by graphing. We checked that off in part A. Tisha thinks she can determine the intersection by solving the system of equations. Try Tisha's method. How can two equations of circles be combined into one equation? What happens when you try to solve? Well, let's look at this here. So, hey, there are a few ways that you maybe have solved systems this year. And I'm going to put those ways down because you should know them. One is the equal values method. Let me just write that down. That doesn't really ring a bell because not all textbooks have the equal values method, but maybe we can think about what that means in a minute or so. So we're talking these are algebraic ways of solving, not using graphs, but actually isolating what a variable equals and then going in and finding the variable's worth in for the other variable by substituting one thing you've already solved for. Anyways, you guys have done this before. Hopefully you know what I'm talking about. Equal values method. And then another one is substitution. If you know what one variable equals or an expression equals, you can substitute that into the other equation. That could help you solve. And the final way of solving systems is elimination. Those are the three algebraic ways that you should learn in Algebra 1 here. And elimination. Can you eliminate in order to solve? And a few different ways to solve this one. How can two equations be combined into one equation? What happens when you try to solve? I might actually, just inspecting this thing real quick, I might actually recommend you solve by elimination here. And I can show that. You also might be able to want to do by equal values method. I'll just do them both because in case you do them both ways, then I want to make sure you know you can do it either way. And then this is just kind of gravy on top of what you're learning. I don't really care if you learn this super, super well here. But maybe we can do two ways. So let's do two. We can do the equal values method. And then we can talk about how you might want to do elimination. So, equal values method. You have a different name for equal values method in geometry than what you have into algebra. Equal values. What do we mean by equal values? Okay, we have one equation. We have another equation. How can we think about equal values between the two to make this, combine this into one equation? Oh, wait, check this out. Check this out. What is the expression on the left equal to? Ooh, it's equal to 0. What's the expression left equal to here? Oh, it's also equal to 0. Interesting. So remember, when one thing is equal to something and another thing is equal to that same thing, you can set those two things equal to each other. What property is that we've been talking about since a lot first semester, not much second semester? What property is that? That's right. This is the transitive property that I'm recommending here. X squared plus 4x minus y squared minus 6y minus 12 would be equal to x squared minus 8x plus y squared minus 6y. So you can set these two expressions equal to each other, the top one and the bottom one, because they're both equal to 0, right? They're both equal to this thing, so they would have to equal the same thing if they both equal 0. So here is what we have, and now we can go about solving this. And so the thing that's going to help us out here, the thing that they made that was helpful for us in order to solve something like this is that we actually have identical y expressions right here. So if I added y squared and 6y to both sides, we actually eliminate y entirely from the problem. Oops, sorry, this is a plus here. So I got to subtract y squared here and subtract y squared over here. And then add 6y over here, okay? So add 6y, subtract y squared from both sides, and that's gonna cancel out any mention of y in this equation. And then we just have to worry about solving for x. So then we have x squared minus 8x over here. Now this is a quadratic, right? We have x squared, we have x's, we have 1's, a constant term here. So what I wanna do is I want to move any mention of x to the left side. And I can do that through subtraction too. Look at this, if I knock out, the nice thing about having the ax squared thing, or sorry, just a 1x squared, it's only dealing with circles that are 1x squareds, is that we can subtract the 1x squareds from both sides, and those are going to cancel out too. So we're just sort of removing equal values from both sides of the equation to get a simpler, easier to solve equation. So now that's all that's left, and the terms on the right side are negative 8x, and then we have 4x over here, and then we have a minus 12. So why don't we add 12 to both sides? This is messy, but hey, we're going to get there to solving if we can follow along and stay organized, okay? So I added 12 over here, got rid of that negative 12, and then I'll just have a plus 12 over here, and I'm going to add 8x right here because I want to move my x's, my positive x's, to one side of the equation. So I had 4x to begin with over here, negative 8x over here. Move the 8x's to where I have more of them, which is the left side. So then I have, on my left side of the equation, I have 12x equaling to 12. So that means x equals 1. When x equals 1, these two equations will equal each other. And the question is now, what would the values of y have to be when x would equal to 1? So that's what we need to do here. So now we're going to plug back in. We can plug back into one of the equations. And the second one looks easier to plug back into. So I'm going to plug into this expression here. But I'm going to set it equal to 0. All right, so I've cleaned up my algebra over here. I've substituted 1 in for x, and I get 1 squared is 1, negative 8 times 1 is negative 8, and then I have a y squared minus 6y. Okay, I got to solve for y at some point. That's the whole goal of this. So 1 minus 7 is negative 7. So I'm going to move that over here, and I'm going to write the left side in a standard form, quadratic form right here. The squared piece here, y being squared, minus to the first power, right? Minus 6y to the first power, minus 7y to the 0th power, right? So ordering it in the order of coefficients, which is the standard form that you write these in. And now I can work about solving this. I can either use quadratic formula, right? You probably use quadratic formula in Algebra 1. You can do that right now. Or I could factor this. So I'm just going to factor this here. And my factoring shortcut for this one is I'm finding two numbers that multiply to negative 7, which would be just 7 and 1, right? And would have to add to negative 6. And that would be negative 7, and positive 1 would add to negative 6. And that would be equal to 0. And lovely, I can use the 0 product property right here. So here, what are the values of x here that would lead to my expression on the left side being equal to 0? Because that's what my right side is equal to. Well, if I plugged in positive 7 for, this is y we're talking about here. Let me change this from x to y. Remember, the whole goal of this was to solve for y. Notice here, this y is our variable now. So if I plug in 7 for y, 7 minus 7 is 0, and that would multiply to whatever this would be, and I would get 0 as my answer. So that would make the equation true. The other thing I can plug in for y is negative 1. That's the other thing I can plug in for y. And that would make the equation true, okay? So now I can write my final answer as coordinate points. The points of intersection. Hey, I just confirmed it right here. I saw in the graph, I checked it in my head, which is fine. But now if I were just to solve this, not have to worry about graphing it, our solution here would be when x is 1, it could equal 7, or when x is 1, it could equal negative 1. And that is my solution right here. Okay, just very briefly, because I said you could have done elimination for this one. This is just because I happened to notice this here, that it had this kind of structure, that if I write both equations again on top of one another, and I wrote this kind of messily here, but the key thing is that what I noticed is that I had y squared minus 6y in both of these equations. And we can actually do that through elimination. What you can do is you can actually multiply this lower one by negative 1, multiply it by negative 1, and then add both equations together. So x squared, multiply the bottom by negative 1, that's just x squared, and then add them together. So x squared minus x squared would equal 0. So that actually eliminates the x squared here, and then negative 1 times by negative 8 would be positive 8, so you'd have 12x's left over when you added the 4x. So here this would be 4x plus 8, right? Because it's basically technically plus negative 1 times negative 8 x, and then that would be 12x. And then y squared minus a y squared is 0. That eliminates here. And negative 6y plus 6y would also bring us to 0. Negative 6y plus 6y is 0. And then we'd have minus 12 left over, because we wouldn't have a constant over here on this other side, was equal to 0. So here, this would have been actually much faster, I think, because then once we add 12 to both sides, we would have 12x equal to 12, and therefore x would have to equal 1. That's where we're going to find our common solutions between the two equations. And then, right, to solve the rest of your system, plug in 1 to the equation, and then you got to solve for all solutions for y, and there are 2 of them. Part C, it says, remember that in math, a function is a special relationship between two variables where each input has a single output. Considering what you've observed so far, are circles functions? And the answer here is heck no. Okay, we've totally seen this here, that for an input of 1, for instance, there is more than one output. An input, an x of 1, returns 2 y values of solutions. You can have at most one output, at most one y value for a given x input here. Okay, so what we've seen here for x equals 1, for example, there are 2 outputs. X could be 7, x could be -1, and those would be solutions on the circle. This circle and this other circle, and that's true for any circle, that they're going to have certain amounts, at least 1, at least 2 really, values of x, and really just infinitely of those x values will have 2 solutions, 2 y coordinates that will go with that x coordinate, not just 1. Fails the vertical line test too, but it's better to explain it from the function perspective, why the vertical line test is a thing, okay? Equation of a circle exit ticket. So normally on a normal year of class, I would this is our 3rd day doing equation of circles. So then you guessed it, we're gonna have a little bit of a mini quiz. And we even have some reading here. So please read this if you haven't yet already. The little math notes. These math notes are good. Just take a second and read them here. And they tell you everything you already know. This is the graphing form. H and K is the center. R is the radius, and it gets squared on the right side of our graphing form. And then we have a general form here, which isn't really that helpful. We have a method to then turn it into a graph. We get something that we don't have our squares completed yet. We can complete the square and get a graphing form and know more about the circle. But here the structure is, if you see this, same amount of x squareds as y squareds. And the highest exponent is 2 in your equation, that's going to be a square. All right, exit ticket here. Unfortunately, we're not really doing exit tickets nowadays, so I'm just going to do it along with you guys this year. But just this is here to make sure you are A-okay with this stuff. Write x squared plus y squared minus 8x plus 6y plus 9 equals 0 in a form that allows you to make a quick sketch of the circle. Then make a quick sketch. Okay, let's do it. I've been doing it all along, but let's do it. More examples here. The more the merrier. All right, C minus for circle, but hopefully got it done. Center's at 4, -3, and radius of 4. So notice here that this circle is actually going to be tangent to the y-axis here because it's centered at 4 and it has a radius of 4. So our radius here will be perpendicular to the y-axis at the outer endpoints of the radius. So that means it's going to be tangent to that y-axis here. 1218, second part. So this is a 3-parter here. Oh, wow. Getting your money's worth on this exercise. On the graph below, the circle, center 4, 2, and radius 3, write its equation, and then a little bit more about stuff, kind of thinking through it like we did in the last one. All right, trusting you guys got this A-okay, so let's just move on to part B. Find 2 points in the circle that are on opposite sides of the circle. That is, they're 180 degrees from one another. Prove, using the distance formula. Ooh, we just learned that a few days ago, that these 2 points are exactly 1 diameter in distance from one another. Yes, 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 yes. Let's do that. So points, I drew in kind of a radius here. Let's draw in another radius over here. So this is going to be 6 units away here, we're thinking, because the diameter equals 6, because we know our radius equals 3. And our points here would be at 1, 2, and would be at 7. So I think what they mean by the distance formula is maybe the fancier of the 2 distance formulas, the one where you're kind of using Pythagorean theorem here. So what we're going to get here is square root x1 minus x2, or x2 minus x1. So okay, so 7 minus squared plus 2 minus 2 squared. Again, we could have just done the absolute value one, but they said distance formula. This is what I think of when they say distance formula. Could have just done the absolute value of 7 minus 1 and gotten 6. That would have been fine to get our answer, but it seemed too easy. So let's just get practice using the distance formula. Well, this would be 6 squared plus, what's 2 minus 2? That's 0. So this is just going to end up being the square root of 6 squared, which is the square root of 36, which is going to equal 6. So it is proven it is one diameter away from one another. Boom, boom, boom. We're good to go. And finally, in our exit ticket here, on the grid below, make a complete graph of the system of equations at right. Well, it looks like they're below here. Then list all points of intersection in the form xy. Confirm your solution by solving the system algebraically. Okay, so let's graph it out first. Looks like this here. Oh, we're not adding or subtracting an h or a k on any of these. So that means our center must be at the origin right here, and the radius must be 5. All right, I think that's a pretty good drawing for number 1. Number 2, ooh, this one isn't a circle. This is actually just a line. Sure, you can have a system of equations where they're not the same type of equations. In fact, the line is going to be a function. The top is a relationship. So sure, you can graph the two out together and see what you get. So let's do that. Y-intercept would be here at 1, and slope would be 1. And it's looking like we're going to have a point at 4, 3 here. Is there going to be another point? Sure as heck there's going to be another point down here somewhere. So let's actually just meticulously graph out where that point's going to be. So we're going to have a negative 1, 0 would be a point, and then negative 2, negative 1 would be another point, and negative 3, negative 2 would be another point. Finally, negative 4, negative 3 would be a point. So perhaps those are going to be our answers. So intersection is going to be, looks like we have 3, 4. That looks like one solution potentially. And then negative 4, negative 3 looks like another solution potentially. And so let's confirm our solution algebraically. Okay, so this one here, I'm actually going to do, hey, you know what? I've reviewed 2 of the 3 solving of systems with you guys. Where did I do that? I did that up here, okay? So I did the equal values method here. I also did elimination here. We did equal values here, we did elimination, and we also solved by graphing. In fact, we just solved by graphing a second ago, solved the system graphing a second ago. We're just not 110% sure because we haven't done it algebraic left. So we didn't do substitution. Let's do substitution. The substitution method of solving here is definitely how I do this. So you do substitution method of solving when you have one variable already isolated. There's no reason to try to add both equations together to eliminate a variable or to do equal values method because we don't know what y is equal to up top. It'd be hard to figure out what y is equal to up top or isolate y up here. That's tough to do. We'd have to subtract x squared from both sides. And then yeah, I guess it would be a difference of squares. We could solve for y, but why do all that work when we could just do substitution? And what substitution is, if we know what y is equal to, then we can take that equal value, that representation of y, and replace it with wherever we see y in the other equation. So if y equals x plus 1, we don't need to have y here anymore because we can replace y with x plus 1, and that's what I'll do down here. So this top equation here, this is the one we want to use with substitution to get us to our answer for x. So x squared plus x plus 1 squared equal to 25. Would be another equation that we would know would be perfectly valid because we used a legal move, which was substituting something that y represents into, and now we can solve. So I would solve this one by first rewriting this here. X plus 1 squared is going to equal x squared plus 2x. Thank you. Plus 1, and that's equal to 25. And then on combined like terms, I get 2x squared plus 2x. And here I got my 25 on this side. Hey, my brain's going. I have to solve a quadratic right here. X is being squared here. So I'm going to try to write this in standard form because then I can use quadratic formula if I have to, or I can factor and use zero product property if that seems easier to me. We can really decide that later. So I got positive 1. I'm subtracting 25 from it. That's going to mean negative 24. And this is equal to 0. So at this point, I'm going to see if this is factorable. Well, there's one thing that I can do to make my life easier here, and that's actually what I can do is I can divide both sides by 2. I notice here that 2 is a common factor of all 3 terms here. 2x squared plus 2x minus 24. 2 goes into all those. 2 goes into 2x squared 1x squared's time. So the 2 would cancel out the 2 here. The 2 would also cancel out the 2 here because 2 goes into 2x. It goes into it x times. So we'd have x squared plus x. And then 2 goes into negative 24, negative 12 times. And you might be thinking, hey, Mr. Fortin, you just divided the left side by 2. That's an illegal move. Well, I'm allowed to do it because I can divide the right side by 2 as well. So that's the division property of equality, that if we have a statement of equality, we can divide both sides by the same amount, and it would preserve that equality here. And then the right side would just be 0 divided by 2, and that's just going to end up being 0. So the nice thing about 0 is you can divide it, and it's still going to be 0. $0 split to 2 people means everybody gets $0. Hooray! And then we get this here, and this is actually something that's going to be factorable. So we can factor it and get our answer very quickly right now. What are 2 numbers that multiply to 12? And it can help us add to 1. Well, 4 and 3 get us to 12, and they're 1 apart. Okay, so that's good. So we need to get to negative 12, so it needs to be negative. So one of these in the factors, right, next to our x's here is going to have to be negative. Another one's going to have to be positive. So we know we have positive x squared, so we're going to have x times x here at some point. But then we got to get to negative 12, so negative something times positive something, so maybe negative 4, negative 3, I don't know. Those are the 2 numbers we're going to work. 4 and 3 get us to 12 and can help us get us to 1. So what we're going to do here is negative 3 here and positive 4 over here, because then negative 3 times 4 is negative 12, and 4 minus 3 is positive 1. Hooray, right? 4 times x is 4x, and negative 3 times x is negative 3x. So you'd have 1x total. When you do 4x minus 3x, it's 1x left over, and that's equal to 0. So here we solve this using the 0 product property. Hopefully you guys are doing that in Algebra 1 here. The solutions for x here are going to be, what value can we put in for x here that's going to make this factor equal to 0? Well, we put 3 in here, then we get 3 minus 3. That equals 0. That's all good there. Okay, so one value for x is 3. That would make a 0 factor right here. And 0 times anything gives us 0. So we know that would make the equation true. The other value of x that's going to make this equation true is if we plug in negative 4 for that x right there. We can plug in the negative 4 there, right? It doesn't matter what negative 4 minus 3 is. If you multiply it by 0, right, negative 4 plus 4 is 0, you get 0 as a product, so it would make the equation true. So 3 or negative 4. Okay, very good. Those are what we got for our x-coordinates in our solutions as we're confirming here. Let's see what our y-coordinate would be. So let's go back to our easier one. Y equals x plus 1 to determine did we get the right answers here. So we got to do this twice, right? Y equals, we can try 3, and this is very easy, 3 plus 1, 4. So do we have a point at 3, 4? We do. We have 3, 4 right here. So we know that this one is true. And what about the other one? Y equals negative 4 plus 1. We know that negative 4 will be a solution to the system, but what about its corresponding y value? And we get negative 3 here. And then this one's true, and that one's true. Confirmed that we have our 2 solutions. And that is that. Graphing circles, completing the square for equations circles in the bag. Exit ticketed it. We've done 3 days of lessons, and we are good to go now. I hope you enjoyed this, guys. I hope you feel like you accomplished something. I feel like I accomplished something. And I will talk to you guys soon. Have a great weekend. Bye.
I don't need to walk around in circles, walk around in circles, walk around in circles, walk around in. Don't need to walk around in circles, walk around in circles, walk around in circles, walk around in. When the ghostly dust of violence faces everything,